Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, we are thrilled to have Nadia Henninger here. She is, of course, here a lot. She is an MSRNE person, essentially, even though she's from Princeton and now from MIT as well. And she's going to be talking about mathematics and side channel attacks.
Thank you. So I'm going to start with a roadmap so we know where we're going with this. This is my walk to work. So I'm going to start with an example of how you can use physical reality to overcome an actual crypto system in practice. And from there, I'm going to move on to how the details of this physical reality interact with the sort of mathematical structure of a cipher. And from there, I'm going to show how some of the techniques that come up in this can actually be extended to much broader mathematical principles. So I've organized things in this way because we're going to start with sort of the real world and then move up to beautiful mathematical abstractions. And so you can see that there's sort of these yellow spikes coming out from mathematics. Henry told me when I showed him this slide that there needed to be rays of truth coming out from mathematics. And then I showed
little pictures of Henry.
That's true. So then I showed this slide to a practical person. They said, are you trying to say we're dirt? And so here's some little gold stars for them. So, and then here's sort of a conceptual map of what I'm going to be talking about. So there's a few themes that are going to be running through this. One of them is sort of modeling the real world in cryptography. Another one is sort of looking at the actual behavior of some widely used ciphers under leakage. And the third one, which sort of runs all the way through this, is looking at parallels between coding theory and cryptography. So the first part of this talk is the cold boot attack. And this was done with a very large number of authors, some of them at Princeton and some of them not at Princeton. So to begin with this, imagine the following scenario. Your laptop is stolen. You're going to start freaking out. But you probably work at Microsoft, so you're running BitLocker because they told you to. And this is good because it means that an attacker can't just take your hard drive and start reading all the files off of it. They've been encrypted. And imagine that you were running for the airport at the time, so you just sort of shut your laptop and threw it in your bag. So your laptop is sleeping. So what are the security assumptions in this scenario that you want to keep you safe? The first is that the encryption is strong, so even if the attacker takes your hard drive and starts trying to decrypt it, they don't have the key, so they can't decrypt it. Now, your computer is sleeping, which means that all the data is actually there in RAM, which means that since your hard drive is mounted, the key is sitting in RAM, but the operating system is actually protecting access to the RAM. And so without proper access to the operating system, since the attacker doesn't know your password, they won't be able to get the key out. And now the attacker might try to reboot to circumvent the fact that the operating system is keeping them away from your computer. But since the RAM is volatile, the key will be lost, right? Mm-hmm. I think you know what's coming. So I'm going to explain the phenomenon of DRAM remanence. So your computer's memory is probably DRAM, dynamic RAM. And you can think of it as an array of little capacitors. And it's filled with data. So when you want to write a bit, you charge a capacitor. And now over time, the capacitor will lose its charge. And so when the computer is on, the computer needs to refresh the state of each bit. And generally, these refresh rates are specified on the order of a few milliseconds. So many, many times a second, the computer is refreshing the state. And of course, when the computer is shut off, then these capacitors will discharge to the ground state. Now, the refresh rates are specified on the order of milliseconds, which means that you can't say that your computer is going to be reliable if it's not powered for a large number of milliseconds. But in fact, electrical engineers have spent the past several decades getting the tolerance of these capacitors up so that the reliability of your RAM is perfect, which means that the average capacitor is going to take several seconds or minutes to actually discharge and lose its state. So here are some, yeah. Yeah?
So are we saying that my machine, while it's sleeping, it's just preserved whatever it's in RAM forever, right?
Yeah, suspend to RAM, yeah.
As long as there's battery power.
So the RAM is still powered.
So why are these capacitors playing a role now?
So the idea is that if your computer is powering the RAM, if I as an attacker tried to go read the RAM by rebooting the computer, then it would be not powered for some amount of time. Or if I tried to take the RAM out and put it in something else, it would not be powered. Everybody's happy? So here's some plots of what actually happens when you cut the power to a computer. So these were generated by writing a pseudorandom pattern to memory, cutting the power to the computer for some amount of time, and then rebooting the computer and looking at the Hamming distance of what was read out of RAM from what was originally written there. And you can see that there's kind of some period during which there's very little decay, and then there's a period of sort of rapid decay, and then it levels off at 50% Hamming distance, which is when all the data is gone because you wrote half zeros and half ones.
And what are these different kinds of data?
So the different colors. So the different colors are different machines. So those were just the machines that happened to be sitting around in the lab while we were doing this research. So these are computers as of a few years ago. And in fact, there were several that are sort of very, very far over here on the plot. They just didn't fit on this graph. So.
And is there some pattern? Do you understand later why certain of them are much slower to decay than others?
So it seems to have something to do with the density of the cells in the RAM. So newer computers, ones with larger RAM, tend to decay a little bit faster.
But not faster.
But there's all sorts of details of how it's constructed. So here is a visualization of what this decay actually looks like. So we started with a bitmap of the Mona Lisa. So say white is a 0 and black is a 1, and wrote that to RAM, and then read it back out again at different points in time, and then looked at what was actually sitting there in memory. And so you can see that this is one of the computers that was sort of way out over here on the decay scale, because after 5 seconds, almost everything is perfect. After 30 seconds, you start to see some decay, but there's still...
What's the banding? What's causing
So the banding is, it seems that some of the cells have a 1 wired to ground, and some of them have a 1 wired to power. So they're decaying in different directions. But and these bands are several kilobytes. So there's a large number of cells in each block that are all decaying in the same direction.
A lot faster, or did I misread these?
Yeah, so I said this is some of the computers, and some of them were like way over here on the decay scale, so that it takes 30 seconds for them to start to decay, and this is one of those machines.
This is just a cartoon. It's not the real image of Mona Lisa that you tracked up.
It is.
It's a bitmap, yeah.
It is a bitmap.
Yeah, so you take the picture, you map it to ones and zeros. So you can see sort of what the decay actually looks like.
Could you produce better pictures by noting the pattern of which ones are going to zeros and ones and correcting those?
I'm not sure what you mean.
Well, because it looks like the top ones are turning back, and so you might want to turn some of them back on.
Oh, yeah. I guess if you wanted to get rid of the bands, then you could flip them.
Probably run as denoising and recover the full image out of the 5-minute thing. But the raw image looks like this.
Well, we'll do that later.
It's
Yeah.
The decay rate is a pure function of just the memory chips, right? It has nothing to do with anything else that's going on in the computer, right?
It has to do with temperature.
Temperature, okay. But apart from that, well, I guess the normal operating temperature of certain machines might be higher than others.
Yeah, if you're running your CPU really fast, then it might raise the temperature somewhat, and you know.
So it's a function of two things: the temperature
It's winter.
and the actual memory chip. So you can.
And there's probably other things, gamma rays. I don't know what else.
Why is this wrong? Why
What?
don't we let
Why
it
does
go
this
on?
matter?
No, I mean, so you know, like, if you want to know how fast...
You don't know much. There's lots of variabilities. That's the physics of it,
Lots of variability
in the decay rate.
Okay, guys.
Right,
Stop there.
Okay.
and
Continue.
you can't look at a certain computer in
You
advance
stop
and
it
say
too.
what
Let
it's
her
No.
continue.
right.
So on the temperature thing, it is very variable for by temperature. So if you cool down the chips in particular, they decay much more slowly. And an easy way to cool them down is to take a can of keyboard duster and turn it upside down, and the propellant comes out at negative 50 degrees Celsius. And so you can spray that on your chips, and then you have very little decay after several minutes, not long enough that you can actually remove the chips and put them into a different computer if someone tries to put hardware restrictions on what you're doing with the RAM. And of course, you can get even colder and have almost no decay after extremely long periods of time, enough to do anything evil that you really want to do. So the main message of all of this...
Google or Google Cup doing something evil?
So anyway, so the main message of all of this is that you can actually get the data off of a running computer's RAM without doing anything particularly special. You can just reboot the computer. Of course, the difficulty is that if you reboot into Windows, Windows is going to overwrite nearly all of the contents of RAM with Windows. And so if you want to preserve the original contents of RAM, you have to write a special low-level program that will not stomp on too much of the memory. And so that is what we did. We have several implementations of it. You can boot over the network. You can boot over USB. You can use an iPod if you want. And so you can get the data in someone's RAM. And so this suggests the full attack that we developed, which...
But what if the computer has decided it wants to first look at the hard drive to boot? So if your boot sequence is such that the hard drive is the first stop.
Then you can go into the BIOS and say, please boot from my USB disk. If someone has set a password on their BIOS and told the BIOS to zero memory, then you can freeze the RAM, take it out of the computer, and put it into your own computer and read it. So the sort of steps of our attack are you take a laptop, you cut the power to the laptop by unplugging it, removing the battery for a second, and then you reboot into a small memory extracting program. You dump all the data from the RAM to a device of your choosing, and then you search through all that data to look for the hard drive keys, fix any errors that might have occurred, and use that to decrypt the hard drive. And yes?
Just out of curiosity, have any of those vendors ever claimed that their system is secure against hardware attacks, hardware level attacks?
So I suppose it's a little bit complicated because the point of having disk encryption is to protect you to some degree against someone who has physical access to your computer. And so I think Microsoft, their first response to us disclosing this to them was to say, we do not claim to have any protection against an attacker with physical access.
But that's ridiculous. Like, that's the point of disk encryption.
Well, so it's yeah.
For example, if the computer is turned off, then obviously you do claim that you can send it away to your attacker, and they can walk at it with anything they want to, and they won't get the data. So, I mean, that's the point of disk encryption. It's when the laptop is physically stolen.
Right, well, for some value of anything, but yes, basically.
Yeah.
Yeah, I mean, well, that's why we don't encrypt the computers here, because they stay in the office.
Right. So
Pressing on.
Pressing on. So we tried this against essentially every full disk encryption product that we found, and it worked against all of them. And In particular, we implemented a complete attack against BitLocker, which was called Bit Unlocker, which was a USB drive that you could plug into a computer running BitLocker and just browse the files.
Now this depends on the machine being running when you get your hands on it. Is that true?
Running or sleeping, or it could be off if you, at that point, had BitLocker in default mode, where it would actually mount the hard drive without asking the user for a password.
The default is that it doesn't ask for a password.
As of 2 years ago.
What good is it at all if it doesn't ask for a password?
No, it asks for your Windows password.
Oh, okay.
But
Yeah,
it doesn't
so-
ask for this BitLocker.
Well, yeah, it would mount the hard drive and then ask the user to log into Windows.
I see.
But
So
by that
it's-
time, you're already in trouble.
Yeah.
I see. So what it does now is, to some extent, in response to.
Well, so even back then, you could say, do not mount the hard drive without asking for a password or requiring some USB stick or something like that. So, fully automated attack. So there are several countermeasures you can take. You can, I'm sure, think of various things that you could do. And all of these are effective to some degree. The problem is that they require annoying the user. They require taking a performance hit. They require new hardware. So it's a trade-off. Now, in the world of, say, more theoretical cryptography, this has a lot of implications. One of them was sort of first observed by Shafi Goldwasser in, I think, her Eurocrypt talk a couple years ago, where, so Macaulay and Raisin, many years before that, had tried to formalize the idea of a side channel attack and they produced several axioms. And among them was the axiom that only computation leaks information. And so she observed that, in fact, this kind of attack breaks this paradigm that the attacker can have access to a key independent of what the computer is actually doing. It's just the fact that you've mounted the hard drive. And so there's been, since then, an enormous amount of work in the theoretical cryptography community trying to design cryptosystems that are resistant to the attacker getting access to a key, even if it's not via some computational mechanism. And so I think you've already seen many talks about leakage-resilient cryptography. And of course, the main argument there is the theoretical cryptographers say, well, if the attacker has access to the complete key, there's nothing you can do. So in order to have an interesting problem, we have to say, well, the attacker can't have access to the complete key. And so they generally work under the assumption that at any point in time, the attacker only learns some imperfect knowledge about the key and then proves things based on that. And yeah?
Just to make sure that if you actually do this freezing and thing, you do have access to the complete key, right?
Essentially, yes. There's very, very small amounts of decay. So yeah, if you perform a cold boot attack in practice, you can essentially get the entire contents of RAM with 0.01% of decay. And so sort of a broader question that I would like to pose is there something in between these two sides? Can you say something theoretically interesting that works as a countermeasure against the cold boot attack, but that wouldn't require some large architectural change to implement, like saying that we have a magical piece of hardware that satisfies the leakage properties that the leakage-resilient cryptography sort of assumes? So that was the first part of the talk. I've introduced the scary world of the real world. So now I'm going to move on to the question of what happens if you do get some decay and show some of the things that you can do there. And most of the stuff in this section is from a paper with Hovav Shakam about reconstructing RSA private keys. So this is to remind us of what's going on. This is a picture of what the decay looked like for the cold boot attack. So as noted before, there's large blocks of bits where all of the bits are decaying in the same direction. And they seem to, you can see some correlations here, but generally the position of the bits that have decayed is pretty random. So one thing you can say, well, if we know that we're in a block that's decaying towards 0 and we read a 1, then it was almost certainly a 1 in the original data. But if we read a 0, it might not. It might have been either 1. So you could think of modeling this as a sort of erasure channel. And that is, in fact, what we do. So I'm going to propose this slightly different model of looking of decay of keys with non-contiguous bits. So you remove all but some delta fraction of the bits chosen at random from a private key. Or another way of stating this, you can flip a coin at each bit of the key, and with some probability the attacker gets to see the value of that bit. And is it possible to reconstruct the key? And note that this is not strictly unidirectional decay anymore, since I've changed the, I'm no longer saying we only get the values at 1 bits, but I've tried the algorithms that we're going to talk about in this section with only 1 bits, and it doesn't seem to make a difference. So now, what can you do with this? So let's start talking about private key or symmetric key algorithms. So AES is the advanced encryption standard. It is the standard symmetric key algorithm. If you encrypt your hard drive, you're probably encrypting it using AES. And so if you think of, well, okay, I have a 128-bit AES key. It's a sequence of random bits. I get some fraction of those bits at random. Is there anything I can do? Well, if you just have a sequence of random data, of course you can't reconstruct anything. But, well, fortunately for the attacker, an AES key is never used in isolation. You're going to be doing some computations with it, so the computer is actually going to be computing a large amount of data based on that key. And we're going to use that data and the structure of that data to reconstruct the key.
So the assumption is not that you just have your hands on the key, but that you have your hands on this
Yes.
computed schedule that's used for
Yes.
fast encryption.
Yes.
This is typically stored with the key.
Yes.
Well, in some places.
All the programs that I listed computed the key schedule, stored it together. That's actually how we found the keys, was looking for the key schedules.
Although I guess one countermeasure that they could use, especially when they go in sleep mode, is because it's just an optimization. So when they go into sleep mode, remove this extra data, and only when you wake up and you really need it.
So that requires.
Or do all or nothing encryption, encoding.
Yeah, so there's a lot of things that you could do if you have the chance to scrub your data before you go to sleep, for example. So the key schedule, so AES's key schedule, what it looks like is you take your original 128-bit key, you run some bytes through the key core, which is, you run them through an S box, you permute them, you XOR them with some other bits of the key, and then you generate a new byte of your next round key. And so you have this whole deterministic structure that you've generated. And so actually this acts as a sort of error-correcting code. And so it's possible to, given an error-filled version of the key schedule, relatively efficiently reconstruct the original key.
So what's the key schedule in this picture?
In this picture,
32 bits or something?
so this is 128 bits. So each of these is a byte here. And this is just a schematic. I'm not trying to get too technical here. But essentially, the relationship between these different bytes is that you take this byte, you run it through the X box, permute it a little bit, then you XOR it with this byte, and you get this new byte of your key schedule.
And so the entire blue and orange stuff on this thing is what's called the key schedule.
You have 11 of these round
And
keys.
you have 11 of those.
Yeah.
And in principle, I see. So I'm just trying to understand the difference between a key and a key schedule.
Mm-hmm. So the key, if you just have this, then you can generate the whole key schedule. So this is your key, and then the key schedule is the thing that you generate from.
And is this round 3 key created from round 2 key?
Yes.
Or is it?
In exactly the same way, plus a little bit of extra.
So, and are these one-way functions?
One might hope.
No.
Not really,
No,
yeah.
it's just one round, so it's
It's a
not a one-way
random
function.
Sort of.
I mean,
features.
so I guess the big idea here is that you're trying to diffuse and introduce errors in, or not errors, but you're trying to diffuse the data as much as possible. And that's what gives you the properties of good encryption. And I mean, one way of looking at this is the way that this gives you a good encryption algorithm by having this diffusion property is exactly the property that makes it a reasonable error correcting code, because you've also diffused all of the bits, and that allows you to correct it.
I think the answer to your question, Christian, is if you have all 12 rounds, maybe it's a good one-way function. But one round doesn't do that much.
Hopefully each additional round makes it better and better.
Right.
People have broken like small round AES, but not the full thing yet. And I mean, if one other thing I guess I want to say is that if you had a perfect one-way function from round to round, then you wouldn't be able to efficiently do some error correction on it, because you would have to try to invert the one-way function in order to get it out again. But in fact, the fact that AES has such a linear structure that you have all these nice XORs here makes it possible to do a relatively efficient decoding of the error correcting code. So, okay, that's nice. That's kind of a combinatorial problem. What about RSA? RSA looks like an entirely different question. It's a number theoretic problem. Is there anything that we can say about it? So just to sort of review what RSA looks like, in order to generate an RSA key, you generate two large primes. You multiply them together to get your modulus, which is going to be part of your public key. The other part of your public key is an encryption exponent, which the only property it needs to have is to be relatively prime to p-1 and q-1. But generally, everyone uses some very small number. And in fact, everyone on the internet uses the same number, which is 2 to the 16 plus 1. And that's 65537. Yes? Oh, okay.
Vary, so how do you know that your 2 to the 16 minus 1 or plus 1 is relatively prime?
It's p, they're even.
Yeah, it's not a good.
So you can, I mean, you can choose p so that you know that you don't have any common factors. The important part about everyone using this same encryption exponent is that e is small enough that we are willing to count from 1 to e, and this is going to come up. So in order to decrypt, you have you calculate a decryption exponent, which is e inverse mod phi of n p-1 q-1. So the encryption is you take your message to the eth power mod n, and that becomes your ciphertext. And to decrypt your ciphertext, you raise it to the dth power mod n. Now, in practice, raising some large number to another very, very large number mod n is not that fast. So what people do is they use the Chinese remainder theorem to decrypt. So you calculate d mod p-1 and d mod q-1, and you calculate those exponents, and then you combine them together to do your decryption. So in fact, any one of these values here on the private key side can be generated efficiently from any other one of them. But in practice, they're all stored together in one big private key data structure. And so all the blue stuff, p, q, d, d mod p-1, d mod q-1, and also the value q inverse mod p.
Why do they need the d if they have dp and dq?
I don't know.
In fact, if you follow the PKCS #1 standard, you must store them all,
Yes.
in fact.
Yes, along with the public key as well. So, so we're going to make our lives a little bit easier and assume that we actually have access to all of these. So we can write down some equations between all these values. So actually, I guess I should say what I'm assuming here is that we have random knowledge of the bits of the variables here that are in red. And everything in black here is public, so we can assume that we know it. And so the decryption problem, well, the key recovery problem is, given random bits of each of these red values, can you reconstruct them? And these are all modular equations. It's not quite clear what you can do with knowledge of random bits. However, in the case of having small public exponent, you can actually transform these from modular equations to equations over the integers. And so I've introduced some new variables here, k, g, and h, which are the multiples in the modular equations. And when e is small, we can actually calculate these values k, g, and h from the information that we have And to get k, you just use this trick from Bonet, Durfee, and Frankel, which says that if you have some knowledge of the upper half of bits of d, you can just run through all the possible values of k, find out which best matches those bits from the part of d that we have, and get that k. And then g and h are just the solutions to a quadratic equation mod e. And so we have two roots. We can try each one and see which one works. So we have some nice equations over the integers relating our values with errors in them. So what are we going to do? Well, so if you read on the internet, you go to the crypto website, and you say, how do I apply to the crypto conference? And it has some advice for authors. And the advice says, well, here's one of the links you might want to read, 10 reasons why a paper is rejected from a crypto conference. And one of the examples that they give is trying to factor some number by writing as a set of binary equations over the bits of the factors. So we're going to do exactly that. Yes. So the way that we're going to solve, so we have this system of equations, and we have 4 equations and 5 unknowns. And what we're going to do is we're going to start at the least significant bit, and we're going to solve the equation for that least significant bit. And then given the solutions there, we can calculate the possible solutions for the next most significant bit and keep going that way. And we'll generate this whole tree of solutions. And you can think about this, if you like algebra, as Hensel lifting. So we're taking a solution mod 2 to the I and raising it to a solution mod 2 to the I plus 1. And since we know some of the bits, we can actually prune this tree when any bit conflicts with our known information.
Is the assumption that we know which bits we know?
Yes. So we know that bit 32 is a 1, and we know that bit 85 is a 0.
Why is that true in real life?
Because we had everything decaying in the same direction. So all of the 1 bits that were left over after everything decayed to 0, we say, well, we know the location and the value of those bits.
Those are the only ones we're counting on.
Yes.
Thank you.
So, so to analyze this, we have a heuristic assumption which says that anytime you make a mistake, so there's going to be one final correct solution at the end, which is the actual solution to our equations. And then we say that anytime we're making a mistake in this branching process, that then all of the next solutions that are generated seem to generate their bits at random. And this is roughly true if you start looking at examples. And so using this heuristic assumption, you look unhappy.
So it's not provable in any way, you're saying?
It seems like the kind of thing that's really hard to prove, that you have this set of equations over some integers, and what do all of the solutions look like if you change 1 bit somewhere?
It's almost certainly true on average, but where number theory isn't able to prove it in any particular case.
And it's used, like these kind of things are used in analysis of factoring algorithms. Often you need to use some kind of heuristic assumption like that if you want to give a good. I mean, it's different to use heuristic assumption, but
so if you make a mistake, it's going to look random.
Yeah.
And if you don't make a mistake, what's it going to look like?
It'll continue to generate a solution.
How do you
that
know?
Will be. What do you mean? How do I know? I know that there's one solution which will have the correct value at any point in time, so it should match all the bits that I've seen.
Okay.
There's one completely correct solution, which is the solution to my equations, which will also be true mod 2 to the I for
And
each
the
I.
heuristic is just saying that once you make a mistake, things rapidly diverge from that.
So that's to
Yeah,
make
I
sure
got
that
part.
somehow these tree nodes don't have too many solutions at each layer. That's where the heuristic calculation is coming in?
Yeah. Well, we know what happens to the number of solutions at each layer. So once we have this heuristic, then that allows us to treat the errors that we make as sort of a random process. And so using tools from probability theory, you can calculate the expected number of solutions that are generated at each step of the algorithm. And since this is a branching process, if the expected number of solutions is less than 1, then you don't expect it to explode into an exponential number of solutions, and the branching process should die out. And this actually predicts that there's a threshold around 27% of the bits known, that below this number of bits known, then you're going to generate a large number of solutions. And if you know more than this number of bits, then your branching process dies out, and so you don't generate too many solutions. So here's an example of this algorithm in practice. Here's a decryption exponent with about 27% of the bits known, and a totally non-optimized implementation of this algorithm takes about 6.5 seconds on my little laptop to get all of the bits out again.
Mm-hmm. So I noticed there are ones and zeros.
Yes.
And they are pretty close together. I thought that you would have large fractions of them would all become the same ones. So I expect large numbers of ones and large numbers of zeros.
So this is me having changed the problem from saying that we only know the locations of the 1 bits to saying that whether we know the values of some bits at different locations, and whether they're a 1 or a 0 doesn't matter.
Okay. Does your analysis depend on having both 1s and zeros?
No. So I've tried running this when you only have the locations of 1 bits, and it still seems to have the same threshold behavior and everything.
Is that large enough to span 1D? Is that large enough to span more than one band of memory, one block of memory?
So this is 4,000 bits. I think the bands, they look different. So it's not that every RAM chip has these same looking bands. It depends, the shape of what you see when you make that kind of picture depends on the actual geometry of the chip. So some of them had smaller squares, irregular things going on. So it might be that a key like this is going to cross some of the barriers between decay directions.
Bits we know are from the original data depend on there being bands, and those bands being large compared to the size of the key.
But if there's a section somewhere in the middle, then you can see that everything to one side of this seems to be decaying towards 0, and everything to the other side of it seems to be decaying towards 1. And there might be some area in the middle where you might not be sure, but you can just play with it until you get it right. Anyway, so this works in practice. It runs pretty quickly, even on a little laptop. And so we ran a large number of experiments on this. So here we generated random keys, took out some large fraction of their bits, and looked at the total number of solutions that were generated. So this tells you the median number of solutions that were generated at each for each fraction of known bits. And then this is the distribution, so like 25th and 75th percentile, and total minimum and total maximum. And you can see that the heuristic analysis actually matches up with reality fairly closely, that sort of above this level, everything just finishes very quickly. You generate almost no extra solutions. And below that level, just the number of extra solutions expands enormously. And we couldn't really go too much further here because it runs really slowly. So yeah. So the experimental analysis justifies, in some sense, our heuristic assumption. So the last part of the talk is going to be looking at some of the techniques for this kind of cryptanalysis of RSA and showing how they extend to very beautiful ideas, especially in coding theory. So at a moral, if not entirely provable level, what the hope was when designing RSA was either that you get a secure public key crypto system, or hopefully if someone broke it, they would break it by coming up with a way to factor, so the world would have an efficient factoring algorithm. And we can't really show this, but we show in the section, oh, I should say, I did this work with Henry all last year. So we're going to show something slightly different, which is that one of the nice cryptanalyses of RSA with respect to partial key recovery actually translates into some beautiful constructive results in coding theory. So in the last section, I was talking about the problem of RSA key recovery when you had something like this. You had non-contiguous bits. You had a lot of redundancy. Ours was by far not the first work on key recovery for RSA. There's a large body of work about the problem of RSA key recovery when you have a large block of contiguous bits of one of the private key elements, and can you do anything with that? So I'm going to be talking about this approach here. So the way that RSA key recovery with, yep?
So just to make sure I understand, when you say redundancy there, this was the fact that related
We have
information
P and Q and D and all of these
schedules and
yeah.
stored and,
Yeah.
and these kinds of
And
things.
here is just if you have half the bits of P, what do you do? And you know N.
And you know N. Okay. Right.
So, so the way RSA key recovery with contiguous bits works is, so remember that we have, and our RSA public key is the product of two large primes, P and Q, and P and Q are secret. So if your adversary obtains the most significant half of bits of P, so we know that P is, the most significant half plus the least significant half of bits. So given the public modulus and the most significant half of bits, can you find the remaining bits of P? And so just to translate this into a slightly more formal setting, we can write a nice linear equation in some unknown x. So the most significant half of bits of P plus x has a 0 mod P. Okay. So the following theorem by Coppersmith, he actually solved this problem in his original paper, but this theorem doesn't quite do it for us, but it's almost what we need. So he says that if we have a degree d monic polynomial and some integer n, that we can find all roots of this polynomial mod n if those roots are small in polynomial time in log n and d. So this theorem, if n is a prime, then we know that we can just solve equations mod primes efficiently. So this is not an interesting theorem. If n, we happen to know the prime factorization of n, then we can solve the equation mod each prime and use the Chinese remainder theorem to construct the solutions mod n. However, if we don't know the prime factorization of n, then that's when this theorem is interesting, because this says that we can do it, in fact, without factoring n. And in fact, if you could solve this without these size constraints on the size of the root, then you could break RSA outright, because note that the polynomial x to the d is exactly, x to the d mod n is exactly the RSA encryption function. So if we could find roots of polynomials of that form, then we could break RSA. So, so that's where these size constraints become interesting. The other way these size constraints are interesting is that even if we do have the prime factorization of n, if n has a very large number of factors, then the number of possible solutions could potentially be exponential in the number of prime factors. So this says it's a constructive method of saying that there are actually only polynomially many small solutions, even in this case. Anyway, so this is a great theorem, but it's not quite what we need. So a small modification of this theorem is actually what we need to solve this problem. So instead of working mod n, we're going to ask for solutions mod some divisor of n. So it says that if we can find, solutions mod large divisors of n by taking a hit in the size of the solution that we can find. And so you can see that this is the problem that we have, where say p is something larger than n to the 1/2, then it says that we can find solutions that are to this equation, where d is 1 and beta is 1/2. It says we can find solutions that are smaller than n to the 1/4, which is about p to the 1/2, so half of the bits of p. So this solves our problem. This is a great theorem. So I'm going to very quickly explain the proof, because it's relevant to what's going to happen later. So the way the proof works in a very broad outline is that we're going to take our original polynomial f and n, and we're going to make a new polynomial so that all of the roots that we're looking for, mod n or mod some divisor of n, are actually roots of this new polynomial over the integers. So that means that we can factor our polynomial over the integers, well, over the rationals, to find the roots. And then we're done. So how do we construct such a polynomial? Instead of asking for roots mod b, we're going to ensure that any root of our original polynomial mod the divisor is a root of our new polynomial mod the divisor to some large power. And we're going to do that by saying that our new polynomial is going to be a linear combination of the polynomials f to the I and to the k minus I. So any root mod any divisor of n is going to vanish k times. And then for this polynomial, if we can bound the size of the coefficients of this polynomial and the size of the roots that we're looking for, then we can bound the size of the polynomial evaluated at those roots. And in fact, if the size of that polynomial is less than b to the k, we know that all of our roots that we were looking for here were our roots of this thing mod b to the k. So in fact, any of these polynomials, or any of this polynomial here evaluated at x0 must actually be 0. And so then we know it's a root of q over the integers. And so then we forget about n and b and just factor the original polynomial. So the question is, how do we find a polynomial here with small coefficients? Well, we'd put the coefficients of these polynomials into a lattice and use lattice basis reduction to find a short vector. And the short vector is going to have small entries which correspond to small coefficients, or coefficients that are bounded. And you might worry that, well, how do we do lattice basis reduction? We use the LLL algorithm.
How do you prove that there exists small coefficients?
So we know that you calculate the determinant of the lattice, and you know that there's a vector of size 1 over the dimension about in the lattice. So we know that there's some vector, and we know that LLL can find a vector of size 2 to the n minus 1 over 4 times the determinant to the 1 over dimension. So you might be worried that there's this exponential approximation factor in LLL. That actually only translates into a constant if you do all the calculations. So this works out very beautifully. This is a great theorem. Right? But of course, that was proven some large number of years ago, so we still have some work to do. The other thing that's great about this theorem is that, so this is a beautiful proof, right? But this actually works in practice, and it's actually very effective. So here again is on my crappy little laptop. We take a 4096-bit n, which has a factor of p, which has 2048 bits, and we erase 800 bits of p. So this part in black here is the approximation of p that we know, and these bits in red are the part that we don't know. And in fact, in 7.5 seconds on my laptop, you can find the remaining 800 bits of p. And almost all of this time is the amount of time that it takes to do LLL on a lattice of 7 dimensions with entries that are many, many thousands of bits long.
But you said we could find 1,000-bit x.
So if you have 1,000-bit x, then you need a 1,000-dimensional lattice, which is not going to happen on my laptop. But theoretically, that's still polynomial time. So what are we doing here? Well, so number theorists are very fond of the analogy of a particular analogy between the integers and the polynomials. So in this analogy, the ring of integers is analogous to the ring of polynomials with coefficients in a field. And so the analog of primes for the integers is an irreducible polynomial for the polynomials. And the right notion of size for the integers is the absolute value. In the polynomial land, a good notion of size is the degree of your polynomial. So once you've set things up this way, then everything sort of works the way that you want it to. You can divide, get remainders, you have unique factorization, you can compute common divisors, you can do the Chinese remainder theorem, which is polynomial interpolation, actually. And But somehow everything in the world of polynomials is a little bit easier. So for example, there's an analog of the Riemann hypothesis over the polynomials, where it's far away for the integers. And yeah, it's a theorem. Okay, yes, there's a theorem version of this. And in general, you can sort of think this is the world of hard cryptographic problems. There are a lot of factoring and whatnot that are very difficult to do over the integers, but over the polynomials, they're very easy. We know how to factor polynomials in polynomial time. And this is sort of this ends up being the world of coding theory somehow. This analogy extends to the idea of a lattice. So you can have a lattice over the integers, which is integer multiples of basis vectors with integer coefficients. And the polynomial analog of this is polynomial multiples of basis vectors with coefficients that are polynomials. And among other things, we have LLL, but there's a lot of cryptographic assumptions that you can't get a constant approximation of the shortest vector in a lattice. But in fact, for a polynomial lattice, you can compute the shortest vector and the closest vector in polynomial time. So we just proved this lovely theorem over the integers, and we have this nice analogy. So let's translate it to the polynomials. So the translation of this theorem to the polynomials, instead of having a polynomial with integer coefficients, we're going to have a polynomial whose coefficients are polynomials in some new variable z. Instead of working mod some integer, we're going to work some polynomial of degree n. And instead of looking for integer or rational roots of our polynomial, we're going to look for roots that are polynomials. And instead of bounding the absolute value, we're going to bound the degree of our roots. So this is nice.
So you knew how to do it anyway, but now the point is that there are few. This proves that there are few of them, or
So we knew how to. Well, this is where we know that in the integer case, we know that we can factor n. If we could factor n, then we could find all the roots. In the polynomial case, where this is interesting is we know that we can factor the polynomials, so we could use the Chinese remainder theorem. But if, again, we have a large number of factors of a polynomial, a large number of irreducible factors, then the number of potential solutions could be exponential in that number of factors.
So the main point of this theorem on the right-hand side is not the algorithm, but just the proof that there are a few of them. And I guess that you can.
Well, and the fact that there's an algorithm is interesting, which we will see on the next slide, which is in fact that this theorem on the right-hand side allows you to do Reed-Solomon list decoding. And so the Reed-Solomon list decoding problem, you're given a set of points. Well, one way of looking at it, you're given a set of points, and you want to find all low-degree polynomials that match a large fraction of these points. And of course, so there's a classical decoding algorithm for Reed-Solomon codes that goes up to the minimum distance of the code. Then, of course, some number of years ago, Guruswamy and Sudan managed to, or came up with the idea of relaxing decoding up to the minimum distance, and said that if you're allowed to, if you're willing to accept non-unique decodings, then you could in fact expand that to a much larger decoding radius, and they gave an algorithm for decoding Reed-Solomon codes up to a much larger distance. And so in fact, the analogy that I presented on the previous slide suggests a new proof of Reed-Solomon list decoding. And we're going to do it by exact analogy to Coppersmith's method. So we're going to generate this new polynomial, which is going to be a linear combination of products of our input polynomials. We're going to bound the degrees of the coefficients. If the degrees are small, then we know that the roots that we're looking for are roots of our original polynomial. And how do we find such a polynomial? We use lattice-based reduction. And in fact, lattice-based reduction, not only can it find an exact shortest vector in polynomial time for a polynomial lattice, but it's actually very fast. And now, if you're familiar with the Guruswami-Sudan algorithm, you might say, hey, this looks kind of familiar because Guruswami and Sudan are also constructing a polynomial that vanishes a large number of times at the roots that we're looking for. But the way that they do it is by stating an implicit condition on the coefficients of the polynomial that they're constructing. And then that translates into a series of equations, which you then solve to find the coefficients of your polynomial. And this gives an explicit construction of the polynomial by saying that it's going to be a sum of these concrete polynomials that we calculate, and we're going to do lattice basis reduction over them. And actually substituting lattice basis reduction for the solving of equations in this proof gives you a time speed up. So we've decreased the running time of read-Solomon list decoding. So we actually took this several steps further. So over the world of polynomials, we can do list decoding of read-Solomon codes. We translated this to an extension of polynomials, which are function fields. And what this gives you is list decoding of algebraic geometric codes. And the analogous extension of the integers are number fields, where this tells you how to find solutions to polynomials, modulo ideals in a number field, which is related to some recent things that have come up in lattice-based crypto. But the big picture here is that there are these powerful analogies that allow you to sort of do arbitrage and get these nice translations of ideas from one domain into the other. So this is my last slide. So where we've gone, we've started from an extremely concrete problem of how to do a side channel attack against actual running crypto systems. And from that, we started looking, that suggested the idea of looking at sort of widely used ciphers under this kind of leakage. And this brought us all the way to learning about these deep parallels between coding theory and crypto. So that's it. So it seems like, yeah, Diffie-Hellman and Elgamal are much harder, that you can't do these kinds of tricks with it. At least I don't know of any way, and there are certain bits of it are known to be hardcore.
Is there a sense of what kind of, what's the minimal computing or architectural assumptions that will allow us to, leaving a lot of redundant bits in RAM seems like an inherently bad idea, especially given what you've described. Is there any nice way, that operating systems can allow you to erase stuff explicitly? Can we actually build a programming language which says, look, this is meant to be for, very temporary use, and erase the stuff that you don't?
People have certainly worked on that, I know. But I think it's a very hard problem, especially when you have people writing code from all over. You probably know about this.
Typically, the way to do business is that the actual crypto and the key storage is done by a library that's part of the system, so you have very good control over that. You don't. Part of good crypto hygiene is you do not let the crypto algorithms or the keys out into the world where the application programmers have their hands on, because they're bound to screw up. So I believe the answer
But within these libraries,
it should be relatively straightforward within one of those libraries to say, you should be able to call into that library and say, I'm going to sleep now, erase the stuff that is dangerous.
Yeah.
I mean, in principle, I think there is no theoretical, principle reason why why the systems have to store the key while the computer is asleep.
Well, there is.
It's just very complex.
Well,
I mean, the most problem is that it's how to bring up the device, to bring up the screen to ask you for your password.
Well, if you forget about the key, then you have to unmount the disk and then ask the user for the password in order to decrypt the key again.
That's presumably unavoidable.
Right. You have
If
to
you're
ask
not going to ask the user for a password, then,
Yeah.
then,
Yes.
then the stuff must be visible.
No, but, I mean, if you only cared about security and you designed your OS around security, then you would be able to bring up a screen that asks the user for a password before mounting the hard drive. But because security is the last thing you think about it, then actually you can't really trust. You don't the device, the driver that brings you up the screen might need a hard disk.
Well, that's not quite true because the BIOS is certainly capable of talking to you without a hard
But they are
disk.
very, very limited. They don't even allow you.
You get
to,
an ugly little screen with no
like
graphics.
Nice thing about like the login screen of Windows might need to contact the network and might need to allow you to type your password not in English and
All those things are true, but
because
so
you
what?
didn't think about security. So the BIOS that can't get non-English characters. Sometimes you do not even I mean, one of the reasons the BitLocker key is numeric is because you don't even trust it to get English characters.
right. Should we continue this discussion now?
No, I think this is probably a good offline discussion. Let's